All right, so today we're going to look at Bohr and Lewis models. These are different ways to represent the electrons in an atom. Uh, each of them has their own ways, but we'll go ahead and dive in with basically just how to set them up, and then we can go on from there and look at how they're useful. So the first thing that we need to do when we're doing a Bohr model, that's the first one we're going to run through, is simply write down the symbol for whatever element it is that we're trying to do it for. The example that we're going to run through together is going to be sulfur. So we're just going to start by putting an S down. That's literally all the first step is. It's just writing the chemical symbol. Then next, we're going to put rings around it. These rings are going to represent the energy levels of the atom. So remember from the Bohr model, which is, that's why this is called a Bohr model, like Bohr's model of the atom, where he discovered that we've got electrons orbiting in certain energy levels and they can't be anywhere between them. And that's what we're representing here with those rings. So we're going to count how many rows, and that's going to be horizontally, like going across the periodic table left and right. So we're going to count rows down. So we simply count how many rows down that element is on the periodic table, and we're going to draw that many rings around the element symbol. Make sure that you don't forget the top row is there, so where we've got hydrogen and helium, just those two little elements, one at each corner. Even though there's only the two elements there, that's still going to count as a row, because the rows on the periodic table are arranged in such a way like that they represent these rings. So for our rings then, we're going to draw 3 rings, again just all around there because it's 3 rows down. Okay, next up. We're going to start placing electrons on the ring. Now it's, again, very simple to do, but just make sure you do it properly because there is a very specific way that it needs to be done. So first thing we're going to do, we're going to leave the outside ring alone. We'll leave that for the next step because things get a little bit trickier there, so it's easier just to separate them out into the outer ring and then literally everything else, so all of the inner ones. So we're going to start by just completely filling in every ring that's not on the outside. A couple things to keep in mind. The first is that the very inner ring, the maximum amount of electrons it can hold is going to be 2. So just simply 2 electrons can go on the inner ring. Every other ring that we have, so if I had a total of 10 rings on there, the first ring could only have 2, but the second, the third, the fourth, the fifth, the sixth, the seventh, the eighth, and the ninth could all have 8. So every ring except for the middle can hold a maximum of 8. So the middle one, again, it can only have 2, so we're going to go ahead and throw 2 on it. Then this next one, because it's not the first ring and it's not on the outside, we're going to go ahead and throw 8 electrons on there. And while you can go ahead and put them in pairs like this, I would strongly recommend you add them in a particular order, because when we do the outer ring, you do have to add them in a particular order. So it's just better to be in that habit instead of accidentally messing up. So that order, and it doesn't matter necessarily which order you go in, but you want to add them one at a time so that there's at least 1 electron in every one of the spots. So the top, right, the left, and the bottom. You want to make sure that you add an electron so that there's 1 in every spot before you start adding them together in pairs. So the way that I like to do it is I like to put 1 on the top, then 1 on the bottom, then 1 on the left, and then 1 on the right, and then go back to top, bottom, left, and right. It really doesn't matter which order you do that in, so you could do top, right, bottom, left, top, right, bottom, left. You could do top, left, right, bottom. It doesn't matter which order you do it, as long as each one of those spots gets 1 electron before you start pairing it. That is very, very important. Again, when you're doing these inner rings, you're going to fill them up so they're all going to be paired anyway, but it's a good habit to get into for when we get to the outer ring. So that outer ring then, the way we figure out how many electrons go here is just simply by looking at the periodic table, and we're going to count columns over, so vertically over. You just go from left to right and count how many columns over it is. However, one of the big important things that you need to make sure you do is you're going to ignore all of the area where the periodic table kind of like drops down. So that's going to be columns 3 through 12, so 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You're going to ignore those because there's weird advanced chemistry stuff that goes on. They get weird with their electrons, so we just ignore them. You won't have to worry about doing any Bohr or Lewis structures for anything in that section, just the stuff that's in columns 1, 2, 13, 14, 15, 16, 17, and 18. So those are the only ones that you need to count. So basically, if it's in column 1, your outer ring gets 1 electron. Column 2 gets 2. Then for the ones that are in the teens, it's really nice and convenient because you basically just pretend that 1 isn't there. So if it's in column 13, it's going to get 3. If it's in column 16, it's going to get 6. Sulfur, if you look at your periodic table, you'll see that it's in column 16. So we've got to put 6 valence electrons around the edges. So we've got, again, we're going to make sure we add this one at a time before we start pairing them up. So if we added 1, 2, 3, 4, now we've got everything else, so now we can start pairing up 1 and 2. So notice, and this is very, very important, that I do have these 2 electrons on the outside alone. Again, it doesn't matter, they don't necessarily need to be on the outside. We could take like this one and put it there instead. But it is very important that every one of the sides has at least 1 electron before you start adding pairs. If you have a pair on a ring and you have an empty spot, that's a bad thing. You've broken some chemistry rules. So just make sure you're doing that. And so that's going to be our completed Bohr structure. One of the big reasons for doing this is it shows all of the energy levels that are in an atom. It shows all of the electrons that are in those energy levels, and then it shows what we've got going on the outside. So this is useful because we can get a fair amount of information from it. It is a little bit tiring though to draw because there's, as you can see, there's kind of a lot going on and a lot of stuff just kind of in the middle there. Okay, so some quick examples. So I want to draw the models for hydrogen, boron, and bromine. So for this, let's see here, get my pen going. Alright, so we're going to start with hydrogen, and I'm going to take like a little break in between each of these, so if you want to do it on your own, you are more than welcome to do so. Okay, so hydrogen, so that's, if you're looking at the periodic table, that's on the very top left. So we're going to start by doing an H, and you're going to have to pardon my handwriting. I'm trying to do this with a mouse, and my handwriting is not the best anyway. Okay, so we start with the H because that's the chemical symbol for hydrogen. Then, next up, we need to add rings, 1 ring for every row that it's down. Hydrogen's in the first row, so it just gets 1 ring. Ignore my thing when it goes off to the side like that. I don't know what's going on, so we're going to deal with it. Pretend that's not there. Okay, then next up, we need to fill in all of the inner rings. But since there are no inner rings, we can actually ignore that. We don't have to worry about what's going on there. Let's try that again. So, since we don't have an inner ring to worry about, now we can move on to the outer ring. Remember, that's going to be based on how many columns over on the periodic table it is. Hydrogen is in the first column, because again, it's in the top left section. So since it's in the first column, it just gets 1 electron on the outer ring. And there we go. That's the Bohr model for hydrogen. Very, very simple. It's definitely the easiest one out of all of them, but that's as basic as it can get. All right, so on to boron. So I'll give you a second to pause so you can go ahead and do this one on your own. Alrighty. So for boron, so again, we're going to start with a B. B for boron. Now we need to count down how many rows it is on the periodic table. So if we count down, we see that it's 2 rows down. So I'm going to draw 2 rings around it. There's my inner ring. And my outer ring. Okay, so from here, next step I need to do is to fill in all of those inner rings. So the only inner ring that I have is going to be obviously that one that's in the middle, because this guy here is going to be considered an outer one. So we're going to go ahead and fill it with its maximum. And remember, the very inner ring can only hold 2 electrons, so we're going to put one up top there. And it's up to you if you want to pair the other one, or if you want to bring it down since it can only hold 2. Either way is fine. Oh, let's try that again. Go away. Okay, so there's the inner rings are done. Now I need to count over rows on the periodic, or count over columns on the periodic table. So again, doing the vertical stuff. And so if I look at boron, I find that it's 3 columns over. So I'm going to do 3 valence electrons. So again, it doesn't matter what order you do this in, but since I only have 3 electrons and there's 4 spots, none of them are going to be paired up, and one spot actually needs to be empty. So the order that I like to do it is top, bottom. One of these days, this might work properly. Top, bottom, and then we'll go to the right. Again, it wouldn't matter if you went to the left, if you left this one blank and you had it down there, as long as you've got all 3 of them alone from each other, and you have them where like one is actually on the top, and they're either in the top, the bottom, the left, or the right. Don't evenly space them out, so don't put like one up here, the one kind of over here, one there. I know some of you would like that kind of symmetry, but that's technically wrong based on how electrons work. Again, that's more advanced chemistry than what we're going to be doing, but it is important, just because chemistry rules, that things are done properly. Okay, so there's boron. And last up is going to be bromine. So again, give you a second or so to pause so you can go ahead and give it a shot on your own. Okay, so bromine. We'll go a little faster through this one. So we got Br. If we count down rows on the periodic table, we can count and see that it is 4 down. Hopefully I don't take up too much space with this. Hopefully your circles, if you're doing this by hand, look a little bit better than mine. Alrighty, now we fill in all the inner ones. I have 3 inner rings on this one. So the ring, the first one, the second, and the third. Remember, the first one always has 2. Then all of the others, are all going to have 8. So there's 1, 2, 3, 4, 5, 6. We're going to get to the point where we're just going to ignore those. Yeah, we're just going to ignore that. Okay, 7 and 8. We're going to ignore that one too. And then again, I've got another inner ring here. I'll add it in a little bit of a different order. Why not? Okay, I can't have 2 of those next to each other. We're going to get rid of both of them. Okay, let's put that one back. Oh, that was weird. Okay, anyway. Oh, no, wrong ring. Ignore me. I'm going crazy. Hopefully that's what I was hoping not to do. Oh, technical difficulties. Okay, real quick. Boom. That's where... Okay. So now we're back to where we were. Sorry about that. Okay, so 1, 2 on that ring. 3, 4. And then I still need to add 4 more. I've got them all individualized. So 1, 2, 3, 4, or 5, 6, 7, 8. Okay, I've got all my inner rings now filled in. Now for the last one, all I need to do is count over columns on the periodic table, and bromine is going to be 7 over. So again, repeat the process just with 7. So there's 1, 2, 3, 4. Now I've got all of them separate. I'm just making that one a little more clear since that was at the weird junction there. So I've got 4 on the outer ring, got 3 more. So let's throw one of them there, one of them here, and let's throw the last one up top. So again, it doesn't matter what order you do as far as top, bottom, left, and right, as long as you give all of them one first and then you pair up afterward. But that's all there is to it. Hopefully you don't have some weird like muscle spasm thing that causes lines like this on yours. But that's all there is to Bohr models. So just make sure you're being very careful going through the steps. Biggest thing people will mess up on this, a couple things. One, make sure that you put 2 on the inner ring and then 8 on all of the other inside rings. People sometimes mess up, put 8 on the inner ring or first or something like that. And then also be very careful to make sure your rings are how many horizontally down you are, and that your outer electrons are how many vertically over you are. Again, that's another simple thing to get kind of mixed up, so just be careful and be on the lookout for that. Okay, so vocab term is valence electrons here. So those electrons that we put on the outer ring are called valence electrons, and they're the ones that are going to be really important when it comes to chemical reactions and stuff. Because they're on the outside ring, they're the ones that are going to get exposed to basically anything first. So anytime you bring another atom in close proximity or in contact with it, those electrons that are going to do any kind of interactions are going to be those valence electrons. And so while all of the electrons in the atom are important because they all contribute to the charge, they contribute to the size, everything like that, whenever it comes to properties in chemistry, the majority of those big important ones rely mainly on those valence electrons. So they are important, which is why they have their own term. All right, so for the Lewis models, and kind of the reason why we just talked about valence electrons, is that is another way to model it, but now we are literally just putting those valence electrons on the atom instead. Oh, this is wrong. I thought I fixed that. There we go. Okay, so with Lewis models, we're going to begin with the element symbol, just like we did with the Bohr model. So again, with sulfur, we're going to throw an S. Then the second and the last step, we just put the valence electrons. Remember, those are the ones that are on the outermost layer around it, just like we did with the last step of the Bohr model. So we count how many columns over we are, and that's how many we put, and we add them on in the same way as well. We do top, bottom, left, and right. Be very, very careful not to put any circles, but that is it. That's all sulfur's that's all sulfur's Lewis model is. It's just simply an S, and you do 1 dot, 2 dot, 3, 4, and then pair up for 5 and 6, and that's all there is to it. So Lewis models, while they don't give you as much information, because they only have the valence electrons on there, and valence electrons are typically the only ones we really care about when we're trying to look at interactions and things, Lewis models tend to be the more used or the more efficient way of doing them. Again, they don't show every electron, so they're not as accurate, but in terms of just trying to model some certain things, Lewis models do everything that we need them to do. Alright, so draw Lewis structures for the 3 of these. So helium, strontium, and tellurium. So helium is going to be on the top right of the periodic table. So we'll start... Oh, let me change my pen color. Okay, so start with... He. Okay, so we start with that. Then next up, we're going to just simply put the valence electrons on. So if you remember, helium is in the second column, because while it is technically, like, you have to count all the way over, if you look at the periodic table, this one's actually kind of a unique exception, because there's no other elements kind of to the left of it other than hydrogen. It's actually only in the second column. So this one is just going to get 2. 1, 2. And that's it for helium. Alrighty. Next up is strontium. So again, if you want, go ahead and pause this real quick so you can give it a shot on your own. Alright, so strontium is going to be Sr, just like it says in the problem. Okay, Sr. Now, if we look at the periodic table, it's in the second column. So this one is going to basically be sort of the same as helium, because this one is like legitimately in the second column, because if we count over, again, we're always going to skip those middle rows with this stuff, but this one we don't even get there. So we go 1, and we go 2. Alrighty, and then that's, again, it for strontium. It's in the second column over, so that's all we've got to do with it. Okay. Then the last one is Te, which is tellurium. So, again, I'll give you a couple seconds, and I've actually got to find out on the periodic table real quick. Number 52. Okay. So tellurium, Te. So finding on your periodic table again, that's going to be number 52. So if we look, that's going to be the 6th column over. So it needs 6 of them. So there's 1, 2, pretend that's 1 dot, that's gross. 3, 4. So again, make sure you add all, the first 4 need to be completely independent from each other. That is an absolute necessity. Alright, so there's the first 4. Then I've still got 2 more to get to 6. So again, it doesn't matter where you decide to put them. Put 1 here, and we'll put 1 here, because why not? And we're going to ignore that line. So again, that's all there is to Lewis structures. It's basically like doing the outer ring of a Bohr model, except all you have to do is just simply throw the electrons on there. But please, please make sure you do not put any rings on the Lewis structures. The rings are only for the Bohr models. If you put a ring on the Lewis structure, that's technically saying that the thing you have is that first shell, or that first ring or layer, or whatever you want to call it, of electrons, and that's technically incorrect. But if you don't put a ring on there, then that means that you're talking about just simply the outer layer. So don't overcomplicate the Lewis structures. Alright, last little bit. Just a little random thing that fits in here. You're going to be doing a lab simulation in, I don't know, sometime soon, kind of over this stuff. So make sure you pay close attention to what's going on here. So light emissions. This works as basically for literally anything that gives off light due to electricity. So anytime that energy, some kind of energy is added, whether it's heat or electricity, those are the 2 big common ones. There are other things that can cause this as well, like ultraviolet light and things like that. But mainly heat and electricity, anytime that they're added to an atom, that electricity has to go somewhere. Remember from your basic science classes, conservation of energy, that it can't be created or destroyed. So if I take energy and I shove it into an atom, that energy has to go somewhere. And what that energy is going to do is it's going to cause electrons to jump to a higher energy level. So remember, just like we drew on those Bohr models, there are all of those electrons sitting at certain energy levels. And so whenever some kind of energy gets added to them, they're going to jump to what's called this excited state, where they go up to an energy level that's higher than where they're supposed to be. However, electrons are incredibly lazy, just like basically anybody else. Would you rather be sitting on the couch at home or out running a marathon? I know there's a few of you who would say marathons. I'd say I don't understand what you're doing, but you do you. But anyway, the majority of us would prefer to be at home just kind of lounging around. And same thing as electrons. They don't want to have all of that energy. They want to come back down into what's known as the ground state, or where their original level is. So basically as close to the nucleus as they can get. But because of conservation of energy, this atom all of a sudden has all this additional energy that allows them to be up there. If those electrons go back down to normal, that energy that they had stored has to go somewhere. And so that energy is going to get released from the atom in the form of light this time, instead of something like heat or electricity. And that light that comes off is going to be could be certain different kinds of wavelengths. So again, if you remember from maybe PNPS or another science class, there's that electromagnetic spectrum where we've got like radio waves on one side, there's gamma rays on the other. In the middle, there's that visible light that's like a tiny little chunk where we can see like the red, the blue, the Roy G. Biv. And so that energy is going to get released from the atom somewhere along that spectrum. And if it happens to be within that visible light spectrum, which a fair amount of it gets released in there, then we can see it in the form of colors. Different wavelengths have different colors of light, and so just based on what wavelength it is going to determine what color that light is. And this is essentially how fireworks work. So in a firework, you could have different atoms, and because different atoms have different numbers of electrons, they have different orbitals, they have the protons are going to, the number of protons in the nucleus is going to be pulling on them differently, which is going to add things to the energy. So because there's all these kinds of unique things about different elements and atoms, they're going to release light in these different kinds of ways. So that's why we can get like blue light from some things, red light from others with those fireworks. So anytime a firework goes up, that energy release is going to be in the form of heat, because it literally catches on fire and explodes, and that causes whatever chemical is inside of the firework to release this light. Because as an electron is, maybe let's say there's an electron and it's sitting on the second energy level here. So all of a sudden, this electron gets exploded by, the firework or whatever. That's going to give it a lot more energy. So it's going to hop on up here to the fifth energy level. Oh, I've never had it do that twice on me before. So it's going to hop on up to the fifth energy level. Okay, this is getting obnoxious. But again, that electron started out at the second. It does not want to stay up here. So it's going to wind up coming back down to the ground state. But again, because of conservation of energy, if the atom had enough energy to throw this back up, then the atom's got to throw that energy back out. And it's going to do so in such a way that when it goes back down, it's going to release that energy in the form of light. And so that light then could be seen as purple, it could be seen as blue, red, it could be ultraviolet, it could be infrared, it could be really anywhere on that electromagnetic spectrum. But the point is that it's going to get released as light when it comes back down. So the big things to make sure that you remember here. Remember ground and excited states. So remember ground states where it's lowest, excited is where it has a lot of energy. When it goes from the ground to excited, there is no light being emitted. It's going to the excited state because there's energy being added to it. So whether that's heat or electricity or something else, there's some form of energy that's being given to that atom that's allowing that electron to jump up real high. But that atom doesn't want all that extra energy. It has to release it somehow to get the electron back down to the ground state. And so it's going to do that by releasing energy in the form of light. So we're turning essentially heat or electricity into light, which is what happens with virtually every form of light that exists really ever, is some kind of energy is getting transformed into light through this process from electrons just moving up and down all the time.